Okay, so when you're watching this today, you're going to see our attempt at doing our very first full duration burn. That's a 60-second burn of our engine, and that's a burn where we burn almost all the fuel out. We've never done this before. We've done engine tests for 5 seconds, 10 seconds, for 20 seconds. We've never done it for 60 seconds. We've never burnt our fuel core or our fuel grain all the way through. And we've never done this with our flight-ready oxidizer tank. This is a lightweight stainless steel tank that's going to be mounted right up this container. While we've taken every precaution, we've checked over systems, we've checked pressures, we've checked the programming. It is still going to be a nail-biting day for us to see if this goes right. If it does, it's monumental. It means we're now ready to start lightweighting the rest of the engine and start building the rest of Starless Rogue.
Today specifically what we're doing is the culmination of months and months of work that have gotten us to this point. So there's integration of our flight oxidizer tank into the test stand that we're operating from over here in Brunswick, Maine. And that flight oxidizer tank is a 26-foot long, 2-foot diameter piece of stainless. And I wish it was that simple, but it has a whole lot of stuff feeding into it and a whole lot of stuff feeding out of it. So it connects to it's in a vertical configuration, our oxidizer tank. And so that connects to a horizontal test motor. But that vertical oxidizer tank needs a containment structure to minimize the risk to the surroundings in case we have any kind of failure, any kind of overpressure event. That was a massive part of what we've been working on, was putting together that containment structure. And I mean, literally massive, because it's a lot of steel. Then the oxidizer tank itself has a litany of components inside of it that help to control the flow of the oxidizer, which is nitrous oxide, out of that tank. And there's been weeks and weeks put into the design, the analysis, and the manufacturing and assembly of that system. Yeah, so what I'd expect to see during this test is there's basically a few phases of this burn. There's the startup, which, like I said, I feel like we've done a pretty decent job of ironing out the roughness in the startup. We ramp up our oxidizer flow rate. So how that should probably look during this engine test is we're gonna light an igniter, or a pair of igniters, and we should start to see smoke coming out of the nozzle of MAREVL. As soon as that happens, that's when we initiate the primary oxidizer flow, but very gradually. So what will happen is there's a term called the choked flow, and it's basically the difference, choked and unchoked flow. In this scenario, it's going to be the difference between a lazy flame sort of billowing out of the back of the nozzle, just sort of coming out and floating upwards. And then gradually we'll go from that to choked flow, which will be a very directed stream of exhaust gases pointed in parallel to the motor. Basically what you'd see in any typical rocket motor in flight, or in a fighter jet engine with its afterburner on. So it's the difference between a lazy flamethrower and a rocket plume. So you're going to see a transition at the early phase of this burn, I'd say between when we finish our countdown to about 20 seconds after that. So as the countdown ends, we light the igniter. We should see some smoke. I think between 10 and 20 seconds later, there should be a lazy flame. And within a second or two after that, it should quickly ramp up to a choked flow and a very directed exhaust plume. At that point, we are producing near peak thrust, because that's when our oxidizer tank will be at maximum pressure. We are using just self-pressurizing at the moment. And so as the oxidizer tank empties, the pressure in the oxidizer tank will drop. But we still hope to maintain a relatively high thrust level throughout the burn. It should definitely stay choked. So from that initial moment of the burn going choked flow until the end of the burn, around 60 seconds should pass, maybe just under that. And towards the end of the burn, don't want to see any drastic changes in the flow of the exhaust. It shouldn't change color much. It shouldn't fluctuate in its intensity. And what the fluctuations in intensity might represent is portions of the fuel dislodging, because basically the way that this rocket motor works is we're spraying a liquid or a fluid oxidizer over a solid fuel grain, and the fuel grain should be burning from the inside out. Basically, if it's a donut, it should be expanding outwards, radially outwards. What tends to happen in fuel grains that are structurally unsound, and what we've seen in some of our tests, is that chunks of the fuel come off, and then instead of just burning from the inside out, you end up burning the fuel from all directions, and that makes it very fuel rich, and you get a sort of darker, sootier exhaust flow, and you get fluctuation in how the plume looks. So after the fuel ignites and we get the choke flow, we'd like to see a steady, very gradually decreasing in intensity plume that's steadily decreasing linearly, or relatively linearly. What we don't want to see is we don't want to see massive fluctuations in that plume. That could start to happen towards the end of the burn or even towards the middle of the burn, and that might be an indication that we need to do some more work on our fuel grain. Minor fluctuations, I guess I'm expecting to see. In a perfect world, it'll just shut off after 60 seconds. In a not so perfect world, we might see some bumps along the way to that. But that's hopefully what we see is that gradual initial ignition, lazy flame, clean plume, 60 seconds, gradually decreasing ever so slightly, and then a shut off at 60 seconds. Our fire suppression system will turn on a water deluge. Basically, we'll turn the rain on above our test stand by emptying a few 600-gallon containers of water, 400-gallon actually, just to soak everything and make sure no fires start. We'll purge some CO2 through our system to make sure we put out any fires that are still happening inside of the combustion chamber, and then we'll go through our procedures to turn everything off safely and hopefully get out there as quickly as possible to see how the hardware held up.
My name is Pete Murray. I'm an investor in bluShift and a member of the board of directors. Very excited to be a part of this team. I've been keeping an eye on bluShift for the past few years, and recently, prior to my investment, I saw Sasha give a presentation at a meeting I was at, outlining the progress, outlining the mission and the vision, and I decided that it was time for me to get a little closer. So I went up and spent a day at the bluShift headquarters, looked at the test pad, spent several hours with Sasha talking about the vision and the business, and decided that now is a good time for me to be involved from an investment perspective and also from a board perspective. The company seems to be is at a stage where the technology is coming to fruition. The vision is more and more tangible every day, and having a diverse team of folks at the leadership level is going to be really a part of putting together the next steps for the business. So I dove in by investing and also offering to become part of the board to lend my effort in a small way to the progress of the business. The space economy is one of the frontiers of humankind's endeavors, from a technology standpoint, from a human spirit standpoint, from an inspirational standpoint, global inspirational standpoint. And we're really seeing the entry of private sector endeavors into accessing and making space more accessible. So when I saw that bluShift was making progress in that area and had a mission that involved actually one of the unique attributes of the state of Maine in the United States, vis-a-vis getting direct access to polar orbit launch trajectories, it seemed to me a way that I could be involved and helpful in what I see as one of the frontiers for humankind, getting easy access to near Earth space and ultimately farther and farther out.
Yeah, this engine test's really different from what we've done before. We've done a lot of short duration burns on the order of like from 5 seconds to 20 seconds. And those were really useful because they helped us characterize how the vehicle starts up, what sort of things we need to worry about right at the point of ignition. So in the past with other motors, we've had some hard starts. And that basically means that your initial pressurization of the combustion chamber happens in an unpredictable and more impactful way than we needed to. So we've done a pretty decent job with this 24-inch diameter motor, using some of the stuff that we learned from the smaller motors of, say, for example, ramping up the pressure in the combustion chamber by gradually increasing the feed rate of oxidizer. So we've got that sort of, we call it a startup transient, that initial moment when the engine builds up to full pressure. We've got that pretty smooth. The next big battle is to see how this motor performs in a longer duration burn, in particular in the mission duty cycle test. So the mission duty cycle test for us is representative of what we'll have to do when we fly suborbitally. And if we can get this motor to burn with performance that's pretty predictable for 60 seconds, that will be representative of us launching Starless Rogue Beta, our suborbital launch vehicle, to space. And so that's a huge milestone. We've been really excited every time we've gotten a motor to light successfully. We've been excited every time we've had a medium duration burn that produced thrust data that showed us that we were getting the performance metrics we wanted to get to. But being able to burn for 60 seconds means that our fuel grain survives and behaves during the burn the way that we expect it to. It doesn't come apart. It means that our injection system, our oxidizer valve body, is going to perform as we expect it to for the full 60-second duration. And it means that we're going to have predictable flow rates and thrust curves that show us that we can achieve our mission objectives when it comes to launch. So our oxidizer tank is a flight oxidizer tank. Our injection valve body is flight hardware. And so we're testing a mix of flight hardware and ruggedized hardware to see how the motor can perform for 60 seconds. And if we pass this test, it means that we're going to go towards integrating into our flight MAREVL, which is basically the motor that we'll be using for the flight of Starless Rogue. We'll connect the combustion chamber and the oxidizer tank and put a flight nozzle on the back end of it and configure it all into a vertical test stand, an extension of what we have out there right now. So this test is a major gatekeeper for us. And if we can pass this mark, we know we can hit the performance with the geometry we have, and then it's just lightweighting and integration. It's going to show that we can make a motor that produces the thrust and specific impulse that we need to get to space.
We are incredibly pleased to announce that we have scored a really wonderful lead investor. His name is Brady Brim-DeForest, and he currently serves as the CEO of Formula Monks, and that's a technology division of the S4 Capital company. As their website says, transforms the world's most ambitious companies with AI. And I know from talking to Brady, he's an entrepreneur in his own right, developed, founded a number of successful startups. He's been heavy in the software development, lean product design, agile development, worked with helping numerous Fortune 500 companies implement processes to enable them to design, build, and ship competitive products at startup speeds, the type of speeds that we're working at. But Brady, most importantly, from our perspective, has been with us since very early days, was an early investor in our WeFund round. He and I think, share a very common passion for space and the developing sector of the new space industry, which is fundamentally the commercialization of space that we're so much a part of. So I apologize, Brady. I did you no justice in introducing you, and I apologize. I've also way under caffeinated for the day and working on about 4 hours of sleep today. So. So everybody, I want to just introduce Brady to you. So Brady, maybe you could kind of share how you first found out about us and what made you decide that you wanted to invest in bluShift and become our lead investor in this seed round.
Good thing. Thanks, Sasha. I thought you did a phenomenal job.
Thank you. Thank you.
But no, really glad to be here. And hello to everyone. I too am under caffeinated It's about 10 p.m. here in London, and it has been a long day. But I'm really pleased that I got a chance to participate in tonight's conversation. As Sasha said, I've been following bluShift for many years. Back in 2021, participated in the We Fund round that I'm sure many of you did as well, and have kept in touch with Sasha and David and the team, and have had the opportunity to spend quite a bit of time with them on site at their facility in Brunswick. And over the last couple of months, have been very impressed as I've dug deeper into the team, their capabilities, but most important, their vision. When I think about the entrepreneurial journey, my own and those that I've had the pleasure of participating in, vision is the piece that ultimately separates the true winners from the rest of us. And without a truly ambitious vision, it's really hard to align your talent. It's hard to align your investors. It's hard to align your clients. And the vision that Sasha has articulated to me, which I won't go into at this moment, but the big picture vision that Sasha is working and has been working for the last 10 years to achieve is really mind-blowing. And it was for me the tipping factor that helped me to make the decision to join as lead investor in our seed round. The interesting thing about the aerospace industry, well, among many interesting things, is the size of the moat. I come from the world of software where the cost to compete against the incumbents is very minimal. You can pull a couple of folks together with some laptops and start shipping code, and you can build a product in weeks and take it to market in months, and cross the penny gap in the same amount of time. In the hard sciences, that's not so easy. Building rockets, building hardware is very capital intensive, and a lot of startups in this ecosystem have spent a tremendous amount of money, a truly mind-boggling amount of money, and that's something that I think is easy to do, when capital is flush and you've got deep-pocketed private equity and venture capitalists that are lining up to invest. And certainly 5 or 6 years ago, that was the case in the aerospace industry. And I think the thing in my own entrepreneurial journey that I've seen is when you're sitting in that position as an entrepreneur, you're under the gun to spend it. You've got to invest that capital extremely quickly, and that leads to a tremendous amount of waste. And when I look for businesses that I'm passionate about investing in, the thing that I always look for is scrappiness. How much can you do with a little amount of capital? And what I've really been impressed by with Sasha and David and the team has been how much they've accomplished with such a small amount of capital, and the level of efficiency that this team's been able to deliver and the progress that they've made with very little outside funding is truly impressive. And so as I started to dig in, I realized that given my experience and my background, I could play a minor role in helping to solve that little part of the problem, pointing, not a ton of capital, but a little bit of capital, Sasha and the team's way to help move us closer to our next objective. And a big part of what I'm focusing on as a lead investor in this round and hopefully subsequent rounds is to bring the right kind of capital into our orbit to help us to bring the smart money that's going to help provide the velocity and the momentum to achieve the next step in Sasha's vision. So thrilled to be here, Sasha. It's awesome to be a little part of this journey that you're taking us all on, and I'm thrilled, really excited for what's to come. I think sky's the limit. Or actually, no.
You got to get beyond that, actually.
That's right. That's right. Yeah.
So our everyday lives are becoming more and more satellite-based. In my youth, satellites were used for long distance communication for very specific purposes. Eventually we got GPS, which is obviously a fleet of satellites which we all use every day in our phones, in our cars, in our boats, in our airplanes. Communication satellites are all more prevalent now. There are several terrestrial observation platforms up there, weather satellites, and ultimately internet satellites, Starlink and others coming into the fore. So our dependence as a society and as a global society on satellite-based communications and other functions is becoming more and more consequential. And these satellites are becoming smaller and smaller as technology advances. And as these fleets mature and satellites become obsolete or lose their orbital positions or just burn out, they'll need to be replaced. And they need to be replaced in the places and spaces where the existing satellites that burned out were operating. And so having a platform that can surgically access points in the sky for replacements of individual or small numbers of satellites is going to become more and more important as time goes on. The current platforms, which are great at taking large number of satellites up to single points in the sky, and then they have to distribute from those drop-off points, are great for populating those fleets, but maintaining the fleets will need different kind of access to orbital trajectories. And bluShift really fits that mission nicely. In addition, because of the nature of bluShift's propellant technology, we will be able to rapidly turn around missions, the kind of thing like somebody calls on Tuesday and we get them into orbit on Thursday for mission critical turnaround of satellite deployments, as well as our ability to move the rockets around through normal transportation means. Because of the nature of the propellant, it's not explosive, doesn't require special permitting and so forth to handle. We believe this offers a significant dynamism to our platform in terms of geographic location and moving around our launch sites and so forth as needed. So all of this adds up to a very nimble surgical access to orbit that we think is a niche that bluShift can play a big part in going forward and complement the large sort of freight train access to orbit that we have with the larger rocket companies. I firmly believe that accessing space and getting off the planet is humanity's destiny. It's part of what drives us and makes us unique as a successful species on the planet is our curiosity and our need to explore and reach out beyond the edges of our knowledge. bluShift is a part of that adventure for humanity, and it's super exciting to be a part of the team. And I encourage anybody who's interested to reach out to myself or Sasha directly or anybody else on the team to follow up with any questions and to get involved.
The next steps for bluShift depend on a few things regarding this test. So it has to have the right performance in terms of, will it give us the propulsion characteristics that get us to space? Will it have the thrust and specific impulse that are substantial enough to get us to space? And also, is it stable enough throughout the burn? We need to be able to burn hard enough and burn stable enough that we can move on to flight hardware, long story short. Ideally though, we hit decent stability and we meet our performance benchmarks, and we can move on to building out the flight combustion chamber and flight nozzle and building that into a vertical configuration. So connecting the oxidizer tank and the combustion chamber and the nozzle, basically all of MAREVL, flight MAREVL that we'll be using on Starless Rogue Beta. We'll extend our containment structure that you'll see during this test that's holding the oxidizer tank right now. We'll extend that another 2 levels, so another 24 feet in height at least, and install our flight MAREVL into that structure. And we'll build probably a concrete ramp or some sort of ramp underneath it to direct the exhaust flow in such a way that doesn't damage the ground and the foundation of the test cell. and we'll start carrying out some short duration tests of the vertical configuration of the motor. And if that goes well, we're going to move on. There's probably going to be a few tests in that configuration. I don't think we'll have to do another mission duty cycle test in that configuration, though all things are on the table at the moment. We're definitely just going to need to do at least a couple of static fires of the fully built MAREVL motor, and then we'll move on to flight vehicle integration and finalizing all the design parameters of the rest of the vehicle that might be impacted by propulsion performance. There's a lot of work to be done after this test. So even though this is a massive milestone, the design and analysis and manufacturing and assembly of the rest of the launch vehicle is to follow. We've basically got, the heart of the vehicle and the oxidizer valve body, and the spine of the vehicle and the oxidizer tank. But we still got to give it legs. We've still got to give it its brain, and we've still got to give it its fingers and toes and all the aerodynamics and aerostructures that are going to be built onto it. So there's plenty of work left to do. But now we've got a beating heart at this point. So whatever comes after that is what we'll find out after this mission duty cycle test. So in terms of performance metrics that we'd like to achieve, we want to be doing around 200 seconds of specific impulse at ignition, and we'll be working our way closer to 250 seconds by engine cutoff. And that may seem really low by the standards of liquid rockets that are out there, and even other hybrid rockets that might be out there. But we're not trying to achieve the highest specific impulse of any rocket. That's not our objective. We're trying to affordably launch our customer payloads to space in a safe and operationally flexible package. So despite those numbers maybe seeming underwhelming, one of my favorite analogies is we're not building a Ferrari to space, we're building a tractor to space. We know we'll get there. We know we'll be able to pull the load that our customers need us to pull up there. And the objective ideally is, as we progress towards a lighter weight Starless Rogue 1.0, is to hit 6 to 8 minutes of zero G time. And so despite the specific impulse being lower than what you might see in other liquid rocket engines or even other hybrid rocket engines, that zero G time that we're estimating we can achieve is a lot higher than any suborbital launch vehicle out there right now can achieve without doing crazy acceleration. So that's another one of our performance metrics, though that's not something that we'll find out from this test. But generally for our launch vehicle, we don't want to be going over 7 or 8 Gs, because that introduces a lot of load, a lot of structural requirements for our customers' payloads. If you're launching at 20 Gs and getting to 6 to 8 minutes of zero G, that's great. You got to 6 to 8 minutes of zero G, but you crushed your payloads, and sometimes that limits the type of research that can be done. Since we're targeting a lot of research customers, it's important for us to launch in a way that's gentle, relatively gentle to the payloads, so that more experiments can be carried out for that longer duration. And yeah, that's what we hope to be able to do with this propulsion system. So despite having the lower thrust to weight ratio or the lower specific impulse, if we can get to space and carry our customers' payloads without causing any damage to them, then we increase the amount of customers that we might be able to serve as Starless Rogue becomes an operational vehicle.
Sasha's enthusiasm is infectious, and when you sit down with him and realize that his expertise matches his enthusiasm, this is a compelling combination and a leader for a business. So for me, that was energizing. The larger arc that Sasha paints for where he wants to go and where the business is going is super exciting. It is initially very practical and based in reality in terms of the booster technologies and near-Earth activities, suborbital and ultimately orbital, but also has a longer-reaching vision of interstellar exploration. It tickles the little boy in me who read all the science fiction books, cover to cover. My bookcase was littered with dog-eared paperbacks of science fiction as a child, and this is the time when we're laying the foundation for those stories to become reality. So bluShift is part of that. I believe that entrepreneurialism requires a level of passion and enthusiasm and overarching value-based motivation to succeed, because these things are hard There are many bumps along the way. And so some of the things that were super attractive to me about bluShift were the fact that bluShift is a pretty scrappy organization. We're not, nobody's rolling around in Herman Miller chairs, you know, in a fancy flitzy office in downtown Manhattan or something like that. This is an outfit that is rolling up its sleeves and getting stuff done. To me, that's a great way to, in a capital efficient way, explore what is a challenging endeavor to get traction with. So those are all attributes that really made me feel like this is more, more likely to be successful than putting my money in alongside a lot of other larger investments into a cushier kind of startup environment.
I'm the CEO of bluShift Aerospace. It's a real pleasure to welcome you all here. We're here in Brunswick Landing, in Brunswick, Maine. So it's been it's really a pleasure to welcome you guys all here to bluShift Aerospace's live streaming of our MAREVL Rocket Engine test. Here at bluShift, we are truly where I like to say innovation is meeting sustainability at the heart of space exploration. So today, this is really going to be a critical milestone in our journey to space. And this test really embodies what must be 10 years of hard work, vision, and our truly unshakable belief that we can bring a more Earth-friendly and cost-effective approach to space launches. The team here has been working tremendously hard. We had folks, including myself, working till midnight and others even beyond, making sure that we've done everything possible to make this a success today. I know many of you are joining us today via live stream, and we're expecting to join us in person a week or two ago when we initially pushed for this hot fire test. But those delays, I think, are all going to manifest itself in success and a really exciting push forward for our company, bluShift Aerospace. So just a little background, our biofuel-powered rocket engine, what we call the MAREVL, is truly a testament to our dedication to developing a cleaner, safer, and reusable technology. So today's test is a crucial step toward that future, not only for bluShift, but for the aerospace industry as a whole. So what you're about to witness is really the raw power, and what I was telling folks out front here who are visiting live, what I like to call the Yankee ingenuity and in our innovation that really drives us forward. So whether you're an investor who's joining us virtually or outside here, the viewing site, a supporter, a public official, or family, your presence here today with us in the live stream or here with us at the site is really a reminder that none of this would be possible without your belief in what we're doing. So thank you very much. So the reason why this test is such an important milestone is that this is the first time we will have run our MAREVL engine for as long as it will take to carry our upcoming suborbital rocket, Starless Rogue, to space, giving dozens of academic, civil, and government researchers the ability to perform cutting-edge research 400% longer than they can do today, than what's possible without the commercial options. So let me give you a quick overview of some of the things you might be able to expect today. So first of all, I will be in and out of the live chat and on the live stream here, and will do my best to answer questions as I see them. Don't be offended if I miss your question or missed even saying hello. I'm already seeing a lot of folks that I recognize, so thank you so much. Thank you for everybody who's joined live here today. So what you're going to see today is we will have a countdown. At 0, it won't be full-on ignition. We will begin ignition, and that takes usually that whole routine takes several seconds. And then you'll see a relatively slow ramp up, maybe slow for those folks who are expecting a quick punch. And then we'll quickly ramp up to full thrust power, full combustion, and the burn will last between 50 and 60 seconds. We're punching it for a full 60-second burn. Again, that's what it's going to take to get to our target apogee for Starless Rogue. But again, and I want to make sure everybody knows this is a static hot fire, not an actual launch of Starless Rogue, but just a static hot fire, our probably most important test ever of the MAREVL engine. It's been over a year, probably a year and 4 or 5 months since we did our last test, and our team has been working so hard for this last year plus, building a vertical containment structure so that we can put not only our oxidizer tank, but in the months to come, our combustion chamber in a vertical configuration, a vertical stack. And thanks to manufacturers here in our home state of Maine, who have helped us build a very capable flight-ready oxidizer tank, a company called Steel Pro. We are testing an important part of our overall rocket, Starless Rogue, in a lightweight, highly, I would say, resilient oxidizer tank. And what we're designing here is not only a rocket to go up once, but to go up many times. bluShift's plans are for to treat sustainability and from multiple approaches. Yes, our biofuel is non-toxic. Yes, it's carbon neutral. But we are planning to reuse our rockets over and over again. And a lot of that, doing that from the onset is such an important challenge for any rocket company. We've seen how many other rocket companies across the planet started off early days, even our country, of throwing away rockets into the ocean, polluting. And our plans are to reuse our rockets and our engines over and over. So our first Starless Rogue will actually be largely a stainless steel alloy that we've worked very hard at designing. So this is just part of it. So what you'll see is that 60-second burn, and then in the seconds and minutes afterwards, I'll be listening in on the engineering chatter to see how we did with the test, and I will do my best to kind of give you guys a download of how that went and what we thought of that test. Now, of course, things don't always go well. They don't always go the way you expect them in the aerospace world. So it could be we have problems with ignition. We had that last time. We think we've resolved them. We've had tests shut down faster than expected and go into a safe position. So many different things that can happen. But I'm supremely proud of our engineering and tech team and all the hard work they put into this, into designing our test site to be safe, to be very, very thoughtful in all the processes and systems we put in place to safely approach this test and to make it a success in terms of data collection, understanding all the dynamics of our systems so that we can be put into in a solid position to build out the rest of Starless Rogue in the year to come and do our first launches suborbitally to space. So thank you guys very much for being with us here today. And for those that are online, please feel free to put in comments. Again, I will do my best to answer them. And folks that are listening to the same live stream, but outside the Mission Control RV here, you can also punch in questions on the YouTube live stream, and I will also do my darndest to answer them. So we are looking forward to lighting this candle and truly taking another step towards the stars. Thank you all very much. Okay, I'm going to try to do my best here to answer some of the questions from folks on the live stream. Let's see. Teo asked the question, what is the tentative launch date? So we're expecting to do a low altitude launch as we wait for our CFR 450 FAA commercial launch license sometime the second half of next year. And some of our customers are wanting to go even on that low altitude launch that might go up to about 10 kilometers. And it's really sort of an engineering launch to test out the systems, test out the recovery systems. That will likely be performed at Spaceport America in New Mexico. And then once we've gotten our launch license, which we expect will take into the following year, 2026, we expect to punch it all the way to space. Red Dwarf is, I think everybody might know now, is really the same MAREVL engines that you'll see in Stardust, just run in clusters. We will have 7 engines on the first stage and 1 engine on the second stage. We're looking to do that 2 to 3 years after the launch of Starless Rogue to space. So this is, all dependent on a multitude of factors, and one of them, of course, is regulatory. But we're very excited to be moving now onto this stage. Really our first move into commercialization. Though when we launched Stardust back in 2021, January 31st of 2021, we did have paying customer payloads on board for that very, very low altitude launch of our prototype using our bio-derived fuel and our smaller version of our MAREVL engine. But truly the real commercialization is in the customers who have signed up already to launch on Starless Rogue. Some of the more exciting payloads that we have on board, we have researchers from universities doing a number of interesting cutting-edge experiments. One is doing a nanobubble research for both cleaning water, for uses both terrestrial and in space, and we're really looking forward to seeing how that works out. They're going to join us for both the low altitude one and the punch it all the way to space one. We also have folks that are wanting to test out potentially liquid transfer systems in microgravity. But one of the ones that it's been around for a long time that we're very excited about is working with a company called Max IQ Space that is building almost like Lego-like electronics experiment projects that students can put together however they want, whichever array of sensors they want, and then they package it up in a CubeSat form factor enclosure and launch it with us. And this really enables students from not only the United States but across the world to launch true space science, build it, design it, build it, launch it, analyze the data, all within one school year, and do it for the same cost as team football jerseys for a typical high school here in the U.S. So we're very excited for that opportunity as well. And really, this is this is one of our many stepping stones. The stepping stone to ultimately get to orbital launches using the same technology that we use in our suborbital rocket, but also a stepping stone into commercialization as we push in from a hundreds of $million a year market to $1 billion a year market in replacing individual small satellites in space, something that really is not feasible today with typical rocket engines. The expense, the cost for traditional liquid rocket engines when it's scaled down just goes up exponentially. And with our reusability, with our simpler rocket engine, with our bio-derived fuel, we're able to do this at a much lower cost than is really feasible today with traditional liquid fuel rocket engines. So we're very excited of where this is going. All right, I think I went far beyond what Teo was asking for, or Teo. I'll move on to other questions here. Okay, so we have It's Duperman asking, awesome. Hopefully you have a neutral burn and no O to F, that's oxidizer to fuel shift or instabilities. Good luck. Yeah, so as with any rocket engine, stability is really important. Dialing in the right blend of oxidizer to fuel at the right moment is really important. We use what's called a hybrid rocket, which I'm sure a lot of you guys know, which is where the fuel is a solid and the oxidizer is a liquid. And this presents a lot of advantages in terms of safety, in terms of ease of design, but it also creates some new complexities. And one of them is this moving oxidizer to fuel ratio shift as you burn that fuel grain, or we call it fuel core, from the inside out. And so you do get a shift of the oxidizer to fuel ratio, but normally, however, one of the many interesting capabilities of our engine is that we're able to very deftly dial in how much oxidizer we let flow into the combustion chamber. And so we've been really thrilled with this technology that we've developed here to do that in sort of a novel, proprietary, and future patented way. So we will see, because when we do this test, this is the first time we will have burnt this fuel all the way through, and that normal oxidizer to fuel ratio shift occurs over time. And we've done a heck of a lot of, and I should say we as in the collective we, because it's not been me, the team has been doing a lot of modeling around how to bring up our oxidizer flow and at what time to keep that ratio really optimized. So yeah, good luck is right, and thank you, It's Duperman. All right, Xander the Space Nerdus asks, has a hybrid rocket engine or hybrid rocket ever attempted an orbital or high altitude launch? So yes, they have, and there's certainly much smaller amateur rockets that have made this attempt at a suborbital level. At a orbital level, to the best of my knowledge, no. There was certainly an attempt to develop hybrid rocket engines have been around for a while, and for many decades, but I know that Aerospace, based out of South Korea, did a launch from a spaceport in Brazil, and that was a suborbital launch. I don't know if any of you guys on the chat know how high up they went. I wasn't able to find any information on that, but that was using a hybrid rocket as well. Oh, high impulse. Has high impulse? Certainly high impulse is looking to do that. I think they're looking to launch from Australia. I don't know if they've made it to space yet. Maybe Eon Space, you can lean in there and let us all know whether high impulse. I think high impulse uses I think paraffin wax and liquid oxygen as their propellants. Ellie Allen asks, what happened to the vertical test stand? There we go. We just brought it back on board with the sun shining brightly just behind it, beyond our logo. So, okay, so it sounds like we don't know how high Aerospace went. Oh yes, AMROC. Yes, AMROC. In fact, one of our technical contacts at NASA when we first developed the MAREVL engine worked there and was part of that. I don't know. Yeah, it was suborbital, right? I don't think that. I don't think they were yet ready for orbital. Bailey Ron asks, is there roll control after leaving the atmosphere? There will not be in the very first launch of Starless Rogue, but there will be in the versions that will come after that. Keep the questions coming. This is great. And also, feel free to correct me on any of the details, especially when it comes to our competition. But I guess another company based out of Australia, Gilmore Space, is also building hybrid rockets that use paraffin wax and liquid oxygen. And actually, I'm not 100% sure they use paraffin wax. They use some solid fuel. And I believe they are trying to punch it directly for orbital launch there from Australia. At one point or another, I think there was the anticipation they were going to launch sometime earlier this year, but certainly have empathy for things take longer than you expect when it comes to launching rockets. And to answer Ellie, or to kind of talk about Ellie Allen's comment there about the vertical test stand. So this test stand was, it's taken about a year to build it to this level. It's a 40-foot tall structure, a whole lot of steel, like tons of steel, and this is all to do things in a very safe fashion. We've seen in other countries what happens when you do vertical tests of rockets and rocket engines, and you don't have the thoughtfulness that I like to say that our team has had about safety, about resiliency, so that things don't always work the way you want, you still can get up in the morning and get ready to do it all over again. Okay, Joshua Breverson asks, what impulse class and average thrust is the MAREVL engine rated at? Okay, so nominally we can achieve between 15 to 20,000 pounds of thrust, and we may actually be sharing that live with you on our live stream today. We'll see how that goes, and it's an experimentation for us. So we're trying to provide some live data feed for you as we do these tests. So we can pop up a bar, a horizontal bar that will indicate the amount of thrust you'll see here. So if you guys are all good with us doing an experiment, and Lindsay here next to me is also good with it, I think we will share that thrust bar. Maybe we can show folks kind of what that thrust bar looks like. There you go. There it is on the live stream. We'll pop that open. This is actually untested because we haven't done a hot fire test with this thrust bar across there. But I'll tell you what, we'll leave this up during the test. If you guys can all just be patient with me, understand this may not work exactly as we intended. Thank you, Eon Space, who said the Innospace's SR-75 reached only 50 kilometers. I'll say only, but that's, I mean, I understand when you're doing a low altitude launch, it is hard to do it all in one grand shot. So while it's only 50 kilometers, I think it speaks well for them. So I don't know how the recovery went, but I'm sure they're going to punch it to space here in the year to come. Okay, I just got an update from engineering. So one of the things that we do is we dial into the temperatures of the oxidizer after it's been transferred to the vertical tank. And right now, we're letting it gently warm up to the temperature we want it to be at. And we're very close. We're about 10% of the way away from the pressures we need and the temperatures we need, so very close. So stay tuned there. Oh, I'll answer this. I apologize. Bailey Ron had asked the question. I can tell you that our specific impulse ranges between 200 and 300 seconds in vacuum. And but it also depends on which vehicle we're talking about. We can run our engines in different configurations, and I think one of the more interesting learning moments for me was that at least with hybrid rockets, sometimes it's not just about designing for specific impulse. It's about designing for the right amount of weight, the right amount of fuel, the right amount of oxidizer. And in our case, for suborbital rockets, we're not trying to create high G loading for our customers' payloads. We're trying to keep it a soft ride so that delicate research can make it to space and back down. So you can dial down the ISP intentionally. I shouldn't say that, this is not the intent, but you can intentionally bring down the ISP and still achieve your mission objectives at a very cost-effective way. So there's certainly a lot of things we are capable of doing today to further increase the specific impulse, or ISP, and we have made some engineering decisions to back it off to make the vehicle lighter and more cost effective. Remember, this is rocket science, but this is also a rocket business, and so we're trying to find this peak operating point for performance, manufacturing cost, and in providing the level of service that our customers want, whether it's suborbital today or tomorrow orbital services. And I think a lot in developing launch vehicles in the past has been all about performance and nothing about the performance. And sometimes the first thing to be sacrificed is the environment, right? Use whatever toxic fuels or oxidizers or cryogenics that are needed to get that rocket up there with the most payload as possible. And from running businesses now for a couple of decades, that it's not about getting the highest performance something. It's about getting the right performance thing that's right for your customer, and is right for your cost, so you can have a sustainable business and sustainable profit margin, and of course sustainable for our planet. So let's see. Ian, the Space Nerd is asking, is the tank still vertical? Oh yes, the tank is very much vertical, and what you're seeing on the camera right now is the MAREVL combustion chamber, and that is the next thing that will be lightweighted. Again, we're going to be using a manufacturer here local to our state of Maine, who's been really fantastic developing high quality stainless steel special alloy products for us to make that lightweight version of the MAREVL combustion chamber. And then that combustion chamber you see on the screen right now will also go vertical. That vertical containment structure will grow by another about 20 or so feet. It was designed that way, and but right now that tower, you'll see if we can pan over to camera 1, that tower you see there on the left hand side contains right now our oxidizer tank, and you can't see it because for safety, and that's why we built that containment structure. That is behind some very large steel doors and louvered panels right now. So but if you look, you kind of look us up online, you can probably see some news articles in the last several weeks, and you'll see some photographs and video footage of that oxidizer tank being wheeled out and put into its vertical position. So now this vertical tank is not just a tank, and as you saw in David Hayrigian, our CTO, commenting on the video shortly ago, there's a lot of engineering that has gone into what's inside that tank, it's another manifestation of the ingenuity of our team and the things we can't get into all the details behind that, but I can say that it is not just a hollow tank. It is much more. So we're very excited to see how this performs, and the last couple of weeks we've seen it perform very well in the cold flow tests, or increasingly so, and hold up tight. No leaks in the tank. We've only had some leaks and fittings leading up to it, but the tank has done very well. Very excited about it. Nicely brought that video of our tank being wheeled out to the test site not long ago. Okay, so let's see. Alan asks, okay, regarding what I was talking about regarding the oxidizer tank, and we can't get into the details and whether is this an issue of ITAR or is this an issue of it being proprietary. The truth is both. Both proprietary. There's a lot of R&D, a lot of science, a lot of research that goes into what we've done today. There's a lot that has happened in the last year that we just can't share. There's so much work that's gone into development of just that tank, let alone the MAREVL engine combustion chamber. So yes, ITAR, and yes, it's proprietary. So yes, keep the questions coming. Thank you guys. And again, folks who are joining us outside the RV, feel free to log into our YouTube live stream, and you can post questions there as they come up. Okay, Altair Blue is asking, curious, is the section on Wikipedia about orbital launches at LC-48 and Wallops true, or just possibilities? I actually don't have Wikipedia open right at this moment. This might be referring to early days intentions to launch from Wallops, Virginia on our behalf. We had a wonderful visit hosted by NASA with many folks from our team to go visit the launch facilities at Wallops. What a incredible heritage launch site that leans in heavily on suborbital research, but also of course orbital launches happen from there as well. So at this time we are not planning to launch from there, from Wallops, Virginia. It is certainly possible in the years to come, while our focus will be launching from off the coast of Maine, it is quite possible that, if not intentionally the case, that we'll be launching our rock suborbitally and ultimately red dwarf orbitally from locations all across the United States, including potentially Wallops. So not currently true, but certainly not fixed, and things do change, and we'll see how things play out over the years. Okay, thank you for your patience. I had to step away and give folks outside the RV here an update on where we're at and to answer questions folks had there. So I'm going to try to lean in here on some of the comments that I've missed to date. Let's see here. Okay, looks like Sophie had asked, if possible, how do you clean the tank after a cold flow test? Is that even needed? So really, it's not needed. We run liquid CO2 through there, and I guess the closest thing we have to cleaning it out is that we run gaseous nitrogen through there before we run the test. So fortunately, the CO2 is easily evaporates and gets out of there, and so there is really no cleaning. Now there was, of course, a lot of cleaning that had to happen to that tank prior to us using it. You know, we there's this whole concept of like it's not rocket science or it's not surgery, brain surgery, but sometimes there is rocket surgery. So we, you know, one of our engineers would literally go down into the tank. I shouldn't. It was held horizontally, and wash and soap that sucker up to clean it out. So there's quite a lot of elbow grease goes into cleaning it. Of course, we use non-toxic substances to do that, of course. Okay. Quick update from the engineering team. We did a test of our ignition system. Folks have seen our tests before. They know that we had some challenges with our ignition system. And I swear this is the thing that has stayed with us for years now. We've, it's different issues with the ignition system, but there was a evolution of our ignition system just last night that has actually made it appear to be much more reliable than even before, after a number of fixes. And they tested just shortly ago, and it's looking good, looking good. All right, so let's see. Okay, Jamie Logan from Tech Place. She asked, can you share with everyone what piece you were working on at Tech Place this past year? What piece we were working on at Tech Place this past year? Yes, so we have been using Tech Place. Actually, we really got our start here in Maine at Tech Place, which is an incubator for, amongst other things, aerospace companies here in Maine, and great facilities, very extremely cost effective. For everywhere from shared desks to access to machine shops, welding booths, large heavy-duty industrial cranes, woodworking shops, let alone conference room, etc. So we're really fortunate to have access to that. But one of the things we used it for, and this is a former naval facility, is we used it to build and to paint quite a bit of that vertical test structure. So a lot of the welding and final finish work before we brought that test structure out to this test stand was done right at Tech Place. And they have, you can go all the way from doing bio companies to biotech companies, all the way up to heavy duty aerospace structures. And we worked with another company called Greason Aerospace that helped us out there as well. They build a lot of test structures there for the aerospace industry, and they assisted us as well as some of our own staff on doing the welding that was involved. So yeah, it's been incredible, and of course it's wonderful to have access to this $1 million facilities, things that we don't have to invest in, but we can use them right here at a much lower cost. It makes it really accessible to start up an aerospace business here in my original home state of Maine. All right, let's see. Hello from Microbyte, who's saying hello from Central Florida. Awesome. I was just there in March. And Mooney the Space Dog says hello from Oxford Hills, Maine. Hello. Hello to you. And Eric Thompson says that poor traffic cone is gonna get it. Well, this means Eric Thompson has been with us for a while, because they know that we have a, let's just say, silicone based oh, that one's gonna get it. Well, we have another I think it's out there. But we have another silicone-based, sort of silly putty-like traffic cone that we made from another traffic cone. I think we put it out last night or this morning. I don't know, maybe it didn't make it out. But it gets beat up during every engine test. It's sort of like that test dummy that gets beat up over and over again but still comes up to play for the next round. So yeah, that test cone is probably going to get pushed right out of there. And Mooney the space dog said, "Let's go, Jerry." I'm going to assume that Mooney the the dog is talking about Gerard. And somebody here in my left ear just told me who Mooney the space dog is. Hey, Alex. A lot of folks behind the team at bluShift, and there's folks and interns that have helped us over the years. We have early days. It started. My first hire here at bluShift Aerospace was Brooke Halvorsen, who's now back with our company after having a couple of years at Running Tide, another sustainable oriented business, tech business here in this beautiful state of Maine. Luke Sandin, our senior propulsion engineer, joined us shortly after. He's here in the RV with me. Brooke is actually located close to the test site at one of the safety positions there. We have Gerard, who's been with us, gosh, for almost since really before, 3 years plus. He's been with us on a volunteer basis back when we were launching Stardust. David Herikian, who's been with me effectively since the beginning, back when bluShift was just a concept. And I was introducing to about 24 people, hey, let's build a launch vehicle and let's do this in a more sustainable way for our planet. And he is now, he's been our CTO for what, I think 2 years now, and has been an incredible force in our team, organize the team in the complexities, the processes that need to go in place to ensure that things like today's tests run as well as humanly possible. We also have on board some of our newer hires that used to be interns, Catherine Kluke and Ben Lemieux, who are mechanical engineering majors, and working on many different facets of the design of our MAREVL engine and also the Starless Rogue, as well as leading into the design of the test site and the upgrades to the test site. And quite frankly, all of us lean in when it comes to elbow grease, working at that test site, turning wrenches, laying down new steel members, etc. Everybody gets involved. Doug has been with us for a number of years, a UAV major from the University of Maine system. He joined us on board, gosh, maybe 3 or so years ago. An incredible force of nature in terms of how much that he gets done, especially with the hands-on stuff and constructing the test site. We also have on board Tom, who's helped us out with so much of the development of our controls and data collection systems. And he's really helped us take it to the next level in terms of that software development that's so critical to what we're not only doing today, but doing tomorrow. Lindsay Becker, who joins me here, is sort of my right-hand person in so many aspects of marketing, interacting with our investors, and organizing events like this one here, this live test. And for the first time this year, was working with an intern we had from Bowdoin College on the marketing sides of really, well, this hot fire test today. Then, let's see, what else do we have out there? Who else am I missing here, Lindsay? I feel like I'm forgetting somebody. Of course, I forget somebody. Russ, who's been with us working on a part-time capacity as our welder, and sometimes very full-time capacity, welding so much of that vertical test stand structure, as well as other members of our test stand. So it's been incredible, and I've skipped over a lot of interns that have helped us over the years, and other employees that have worked with us over the years, and have really gotten us to where we are today. Years ago, I was working with Seth, who right here in the same RV was helping us do the same broadcasting and live updates, and providing really funny and fun nuggets of space-related facts and funnies. All right, let's see if I can get back to some of these questions. Jason Cutter had asked, are there still opportunities to invest in bluShift? So the very first time that we provided the opportunity was we actually used an equity crowdfunding website called wefunder.com, and a lot of folks that I know invested directly in bluShift in early days. Since then, we've done some other private rounds, including a convertible note, which we just wrapped up just very, very shortly ago. And we're about to bounce into our next round of fundraising, and this will be our first priced round that's going to be happening here in the months to come. So if you want more information, you can certainly feel free to reach out, and we're reach out through our contact us on our website, and we can share more details about that with you if you're interested in this upcoming round of investments. I'm going to say that we were very happy because in this last round we were looking to raise $1.1 million. That's a private investment dollars to match a federal grant that we had received, and not only did we hit that goal, but we went over it to about a little over $1.4 million were raised. So we're very, very pleased with where we got with that fundraising. All right, we have hello to Howard Jones out in Harpswell, Maine. But I just want to say hello to Howard Jones in Harpswell, Maine, next door town. This is very close by. Okay, why? Okay, Tio Mass video asks why have we reset the countdown? Yeah, so as we were getting updates from engineering, Lindsay is quickly updating the countdown clock. And I just want to say that when it comes to countdown, this is not going to be down to the second accurate. And we'll probably get rid of that clock so that we can give you a manual audio override. And just to remind folks, this test with the countdown, what happens, the first thing isn't like bam, ignites and we've got full thrust. The ignition occurs, and then we ramp up thrust, and then it lasts about 60 seconds. It all goes well. Control Alt Power. It says, let's go, no rain. Should fire right up. Yes, thank God. Condensation is not fun for any rocket company. So we're very happy to have almost solid blue skies, but a little bit of cloud's actually not bad. It keeps things from heating up too much for all of us in this not so well air-conditioned RV, as well as the folks outside here. But more importantly, it keeps things nice and dry for all those valves that could get a little sticky when it comes to condensation. And Mooney the Space Dog says hello. Go Luke. Heck yeah. Let's go bed. Oh, Sophie must know bed. That's wonderful. And Rod. Control Out Power asks, any plan to hire for Steuben anytime soon? So our plans are to launch off the coast of Maine, just outside of Steuben, and our plans are to build our manufacturing location there in the town. It's an incredible, I think that Yankee ingenuity is a real thing, and here in Maine, I think we embrace it more than anywhere else, especially in rural Maine. One of the things that I learned by going up to visit these potential launch sites is how many capable individuals there were in the Washington and Hancock Down East area of Maine. And these are folks who are working with composites and welding every day as if it's nothing. Well, it turns out those are the same abilities and features and capabilities that we need to build rockets. And so we're really, really excited to have this opportunity where we can create a way of providing back to the same town and area region from which we'll be launching in. And at the same time, we have such an incredible human capital wealth there at that part of Maine that is so capable of doing exactly what we were going to need on a manufacturing level. So, so the idea is that we'll ultimately be hiring between 100 to 200 people in our company as we ramp up over the next several years. And when we go to our Series A round of funding, which will probably happen no sooner than next year, my expectation is that round of funding will kick out our ability to now, start building our manufacturing facilities there in Steuben. So we're very excited for that. Right now, we're not hiring there. We're still a small team, and right now we're not doing more than one-off manufacturings. We're honing in the technology, and then we've rolled over to refurbishing our engines and manufacturing them from new. So please do stay tuned. We're very much looking forward to the day that we can finally break ground in Steuben and take advantage of all those talented individuals there in the region. David Swenson asks, greetings from New Jersey. Have you looked at the maritime launch site in Nova Scotia? I haven't looked at it personally, but I know of it. In many ways, it's sort of a competition to exactly what we're doing. But it could also be an alternative for us as a launch site, or a way for us to expand our launch capabilities. It is really duplicative of what we want to do here in Maine, because as we can here off the coast of Maine, launch directly into the #1 orbit for these tiny satellites. This is a $28 billion market. Half of that market is just for launching into polar orbit. Polar orbit is where you're going around the poles, North and South Pole. So Maine, with its southern-facing coastline, allows us to launch right over the ocean directly towards the South Pole, oddly enough, or ironically enough, and enables us to provide our small satellite customers with absolute direct access to polar orbit instead of having to go into a much larger rocket and slowly migrate their satellite into the correct orbit. We're really providing sort of an Uber-like, that's an overused term, but like a taxi, direct, dedicated launch service for these customers in the years to come. All right, we're going to pop up here for you guys. I said that we can't see from the outside of that vertical test structure the oxidizer tank, but here I can share with you inside of you. Now this is, of course, all covered up with insulation and reflective tape and insulation, but that is a very small portion of the oxidizer tank, and the way we have it mounted allows us to know how much oxidizer is flowing out by weighing that whole tank dynamically. And so that's actually on a flexible bellows system that allows us to dynamically weigh how much that tank is at any point in time along this test, as well as allowing us to see how much oxidizer is loaded leading up to the test. So there's a little picture, you know, we don't have a good camera view that can give us the full view that we can share online, but I can give you a little demonstration of what that oxidizer tank looks like when it's covered up with a lot of insulation. And the oxidizer tank even did a little wiggle for you there. Here's another view of our vertical test stand. You can see the louvered portions of the test stand on its sides. There's 3 sides that have this louvered structure. The side that's kind of facing towards us has the panels, and that's where we bring up the tank. These are all very thick members of steel, and this structure is designed so that should anything happen, it allows the pressure out, but contains everything very safely. So we're, you know, what you can't see here is on top is many tons of steel, probably not many tons, but several tons of steel at the very top that contains everything vertically as well. And again, I'll just kind of remark that if you kind of look at aerospace news in the last few weeks out of China, you can see what happens when you don't have a containment structure around your test site. So again, I think this is sort of proof to the innovation, ingenuity, and the hard work and the concern for doing things well and doing it safely by our team, and you know, very proud of all the hard work that went into the building of this vertical containment structure and its ability to scale with us as we scale our testing capabilities. right, thank you guys very much. Okay, things are looking very good. The system pressures and temperatures are just about exactly where they need to be, and they're doing some final resets and clearing the control system. So I expect, from what I'm hearing from the team, that we are just a few minutes away. So stand by, stand by. And we'll again, that clock is just sort of a, it's sort of a more or less estimate of what it would be, and we'll make that clock disappear on the live stream and give you an up-to-date audio countdown for folks. And remember, the countdown is countdown to when we begin the ignition sequence. We don't have immediate thrust. It takes a while for the ignition sequence to complete, and then we kick on to the injection of the oxidizer. So it's not your typical rocket launch, or rocket launch, or certainly rocket engine test, in that 0 does not equal full thrust. It takes a few seconds. Hello to Rory, a former intern of ours who worked very hard here. Big hello to Brady, our chairman of the board, calling in, saying hello from London. Hello, Brady. Back to Brady from the team who I just yelled across the way to say that you said hello. And there's Peter saying the same thing, another one of our board members. And yes, and hello to Marco from France, who's been doing an incredible job of covering our tests in over the last couple of years. Hello to Marco. I only speak Spanish and English, so I guess I don't even know how to say correctly how to say hello in French. Bonjour. Okay, I just leaned back in my chair and punched the door open to get an update from David, our CTO. And looks like we're just a little light on the pressure, so that means we got to get our temperatures up just a touch. So just a touch. Just a few minutes away from getting this going, and but it's still looking good. But we really want to hit on our dialed-in pressures, because if we can simulate how we're going to do this in launch as closely as possible, the better. We really want to nail these numbers in just right. So Mother Nature's doing a great job helping us warm the tank just to where we want it. So I apologize for the delay, but I really appreciate all of you guys being so patient, listening in, and this exciting, monumentous milestone for bluShift as we push forward for our full duration burn of the MAREVL engine, a burn that will enable Starless Rogue to its first leap towards the stars, a suborbital rocket that will go higher and longer into microgravity than any of the commercial offerings out there today. So stay tuned. Almost there. Hello to Mark Cole. Hello, Montreal. Sam. Mark Cole asked the question, what's the expected weight loss on the oxidizer tank? So, let's see, I was just looking at that number. I think we are burning through about close to 2,000 kilograms of oxidizer. Yeah, the sunset here is absolutely beautiful. Gorgeous here in the city of Maine. Perfect temperatures too, perfect temperatures. Ooh, Dwayne Ebersole asks, with the sun setting, how bright is this going to be? Gosh, you know, that's a good point. That having the sun now behind the trees means we're going to be able to see this test even better than before. That's a really good point. Looking forward to it. Lesh 709 is right here watching from downtown Brunswick. All right, rock on. Ooh, and hello to Garrett. Nice name, I like to see. We have the folks outside the RV are very patiently waiting. We are providing some food and beverages, but can't do that online so easily. So I hope you guys are all pulling up some dinner, something to drink at home or wherever you may be, and tuning in. Thank you. are 0.03 megapascals away from our target pressure, and it is slowly creeping up to where we want it to be. So target pressure is just very, 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 very close. Almost there. Almost there. Thank you guys for your patience. Stockholm refers to a Fat Boy Frappe, which was just frappe was just at the northern end of our runway on Bath Road. A real well-known site for the summertime appreciators and lovers here in Maine. Let's see. Marco comments, nice to see us again. It's been a long time since the last test. Yes, it's been way too long. We've been working so hard. It's been tough because we can't, so much of the stuff that we're working so hard on we can't share that we want to. But this accumulation of hard work and effort does allow us to get to this point in sharing this test. So yeah, it's been long. I expect our next test will come in shorter order. So but it won't take a year and a half to get there, or a year and several months. Okay, Brady asked the question, once we reach pressure, how long before the burn begins? Once we reach pressure, we're talking just, you know, we begin the countdown sequence. So it becomes minutes. They have to do safety checks. It's basically a series of checks and processes to make sure everything's good and clear. We call in the local firefighters and our police force here, notify them that test is imminent, and amongst many other things that they go through for the whole checklist, and then test. And I'll try to do my best to kind of keep you guys updated as I keep at least one ear open from the engineering team. Magno him asks, hello from Southern Maine, hello. I was wondering what the thrust output of the MAREVL engine is. So the thrust output is about 20 kilonewtons, peaks out around that. And we'll see it go down a little bit. We've done a lot of work to control the flow of our oxidizer so we can really flatten the curve in this hybrid rocket engine. And it's going to be very interesting to see how it all tunes out. It's going to be very interesting. Eric Sauter asks, what is the fuel for this rocket? So the fuel is proprietary, but I can tell you this, it is a solid fuel. I discovered this, sort of the basis for this fuel on my brother's farm in North Yarmouth, Maine. He's an organic farmer, and basically sort of serendipity led me to discover this substance and wonder, could it be used in a hybrid rocket engine, this solid fuel? And what I found out is that not only did it work, but it worked better than the petroleum version of the fuel that I was using at that very moment in time in these small hybrid rocket engine tests. So very, fortuitous, serendipity, whatever you call it. But I think that's how a lot of inventions are done. You're open to the moment that there's new information, and you wonder what it can be used for, or how it can be used, or improved upon, and that's essentially what happened. So that's that substance, which is part of the proprietary mix, is still used today. And if you think about the other fuels that rockets are using, most rockets use still today RP1, which is basically refined kerosene, so petroleum, stuff that you don't want to see find its ways into our oceans or let alone land. Most commonly, liquid oxygen is used, cryogenic oxygen, which itself is not toxic, it's just very dangerous. One of the things that we try to do here, as you can see, is do things in a safe fashion, and choosing our oxidizer and not working with cryogenics has been able to enable us to do things at a much lower cost, and enable us to really move at a quicker pace than I think we could have otherwise. Stand by. right, guys, the moment's here. We're finally here. This is it. We're down to the last remaining seconds. The countdown will begin shortly. Stand by. Here we go. Come on, Marvel. Now we're just waiting on Aaron to turn around us. All right, we're just waiting for the, right now, one of the delays, because sometimes it's not about us at all, it's about airplanes flying in and out of this executive airport. So we're waiting for the plane, air traffic to clear here before we hit the go button. And as Adam, my neighbor, would say, let's go, I'm sure. Sorry about, thanks you guys for the mic check on the audio here. We're waiting for the air traffic to clear, but we are ready to go as soon as that air traffic is clear. Stand by. Now we can see the thrust bar on the bottom side. Lindsay's just enabled it. And, all right, some pre-checks. That was incredible. It was really incredible to see. I still wish I was much closer. What you see right now is the carbon dioxide system. Oh, right, we're seeing right now is the safety valves opening up just to get our system unpressurized. But that was actually a successful test. We saw some instabilities in the middle there, and we're going to be really curious to lean on the data, see what was there. But this was amazing. We met our 60-second goal of burn time, and that was our key goal to hit. So it was something else. Can't wait to hear the results of the data and make the next test that we do even better. Very excited for all the hard work this team went into doing. I want to thank, big thanks to our investors, big thanks to the public, big thanks to especially our team and their families for all of their patience in allowing us to work many late nights and weekends to get to where we are today. And thank you all for joining this today. Look forward to sharing another live stream with you all in the months to come. Thank you very much. Have a wonderful day.